Okay folks, in this lecture we're going to take a look at the product, quotient and chain rule for differentiation. First of all though, we'll just have a quick recap of the rules we've encountered so far. All of these are available in any kind of formula table. You'd always have these in the exam. If y is a constant, its derivative is 0. If we have a constant multiplied by x, the derivative is just a constant. And I've explained all these in the previous lecture, so I won't go into any more detail. The power rule. If we need to differentiate a power, bring down the power and add -1 to the old power. The derivative of sine x is cos x. The derivative of cos x is minus sine x. Derivative of the exponential function e to the power of x is itself e to the power of x. And the derivative of the natural log function is 1 over x. So we'll see these. I won't really go over them again, but we'll just introduce these in the coming lecture again. First of all, we'll take a look at the summation rule. We met this in the last lecture as well, but I've included it here again for completeness. So this is if an expression has several terms been added or subtracted, then we simply differentiate each term separately. So u is a term, v is a term. We simply differentiate each term separately. And I have an example on the next slide, so we'll take a look. Remember, we could have a minus in there, and that would be dw, dx, etc. So we're asked to find the derivative of this function here. So there's two terms. There's this term, and there's this term. So we're going to call the first term u, and the second term is v. And now we just differentiate these independently. So this one, first of all, when we get the derivative, the constant stays, and then we're just differentiating x squared. The 2 comes down, and we add -1 to the old power, so it becomes 2 to the power of 1. So dy dx in that case is 6x, or du dx, sorry, to be more precise. Similarly here, we're calling the second term v. Again, when we find dv dx, any constant stays, and then as we saw from the previous slide, when we differentiate sine x, we get cos x. And now the rule simply states our overall derivative is the sum of these. So we just add these terms. Because there's a plus sign in here, we add them here. So we've encountered this rule already in the last lecture, but it fits neatly in here as well, because in the next rules we're going to take a look at what happens if two terms are being multiplied. We use the product rule. And then what happens if two terms are being divided? We use the quotient rule. And the setup is the same. Identify u and v, differentiate each one separately, and then feed them correctly into the formula. So now we take a look at the product rule. If an expression to be differentiated consists of two terms being multiplied, then we use the product rule. So here we have, notice now the sign has changed. It's now two terms, u and v are being multiplied. And the product rule looks like this. dy dx is u dv dx plus v du dx. And again, it looks complicated, guys, but once you see a couple of examples done, it's fairly straightforward. The product rule would always be given to you as well in the formula tables. So we'll take a look at an example. So now we have the same two terms from the summation rule, but this time they're being multiplied. So we're looking at u again. U is the first term. v is the second term. We differentiate each of these as before. And now we have the four elements. So it's u dv dx plus v by du dx. So it's him by him plus him by him. So when we write it out, there is u dv dx plus v du dx. Now finally, there's always an order in which to write things. So numbers do, 3 by 2 is still 6. Be careful here, 6x, this will come over to the front. So this sine x, that x in there is protected. The 6x would not multiply the x become by x squared, it moves to the front. So it's very important to realize that, guys. Anything that's directly after a cos or a sine, it's shielded by this cos. You can't get in the back door, so to speak. So when we tidy up, 2 by 3x squared gives us 6x squared by cos x. And now it's 6x by 2, and that gives us our 12x. So it's always good practice to try and tidy up the function as much as you can. But stop where you feel a little bit uncomfortable. If you feel you might be breaking any rules, it's nearly better to leave the function like this than to write your final answer incorrectly. So we take another look at the product rule now. Oh, sorry, I've forgotten there's a common term here. 6x is common to both of these. So we take it out. So 6x, so this is just factorization. We looked at this in semester 1. 6x by x cos x, and then 6x by 2 sin x. So this is just the neatest way, This is just the neatest way of writing that expression. So now we're asked to find the derivative again of two terms being multiplied. So we have u multiplied by v. So we'll call the first term u, the second term is v, and then we differentiate each one separately. So when we differentiate this, the 2 stays, the power drops down, we reduce the power by 1, so that'll give us 6x squared. And here then, when we differentiate 4 by e to the power of x, again the constant stays. And when we differentiate e to the power of x, it stays the same. So it actually looks the same. And that's the property of the e to the power of x function. So now we take a look at the rule. We have the 4 elements. So it's u, sorry, I should just say it's this bit, so it's 2x cubed u dv dx. So it's 2x cubed multiplied by that, plus v by du dx. So you just kind of slot them all into the formula, each of the 4 little blocks. So here's u dv dx plus v du dx. And we'll take a look, 4e to the power of x is common. And actually, well, first of all, we'll multiply them out, sorry. So this 4 will multiply by the 2. That gives us 8x cubed e to the power of x. Always write x first whenever an expression. Don't write it 8e to the power of x, x cubed. X kind of gets priority. Numbers, it's the sign comes first, then the number, then the highest power in x, and then any functions in x. That's the order in which you write anything. So it's sign, number, x to any powers, and then any other function, be it cos x, sin x, e to the power of x. So this is the order in which you write any term. It's the, there's kind of a a hierarchy in how you write things. So we bring the number to the front. That's what gives us the 8, 8x cubed by e to the power of x. And again, these move in here, so the number moves to the front. 24, 6 by numbers do what numbers do. 6 by 4 is 24. X squared, and then e to the power of x. And finally then, if we take a look, what's common to each term? Well, in terms of numbers, well, 8 is common. We're looking to factorize here. When we look at the x bits, x squared is common to each, and then e to the power of x is common. And here, it's multiplied just by x. That's what gives me the x cubed. And here it's multiplied by 8. So it's always good practice to factorize if you can. I thought my color was a bit off. And there's the answer then correctly factorized. But in Moodle or anything like that, either of those answers would get you the marks because they're both correct. Just the bottom one is a little bit more neat in terms of maths. Now we'll take a look at the quotient rule. So if two terms are being divided, then we use the quotient rule. So it's the exact same setup as the previous examples, the summation rule and the product rule. But the derivative is just a little bit more complex. V du dx minus u dv dx all over v squared. But it's the same process. We identify u, we identify v, we differentiate u, we differentiate v. And they're the four building blocks then of the quotient rule. So it's really a case of identifying u and v, differentiating them, and then slotting your kind of answers into the correct part of the rule. And this rule again would be available in any formula tables. So it's kind of the same two terms from the previous examples, but this time they're being divided. So again, u is the term on top. You don't have a choice. U is the term on top, v is the term on bottom. So u is 3x squared, v is 2 sine x, du dx is 6x, dv dx is 2 cos x. So again, now we've our four building blocks. And now it's just a case of putting them in to the correct place of the quotient rule. So it's v du dx. So it's v him by him minus u by dv dx. That's the top line. V du dx minus u dv dx. Then on the bottom, it's v to b squared. Now remember, when we're squaring this, each bit gets squared independently. So 2 squared will give us 4. Sine x to b squared gives us sine x squared, which looks like that. And now we just look, we have 3 terms, 2 on the top, 1 on the bottom. We just look for something common. The only thing that's common to all 3 terms is the number 2. So we divide the top and bottom by 2. And here is our simplified version. But again, both of these versions are mathematically correct. It's just the one on the bottom is a little bit neater. We look at another example. Here again we have u 2x squared cubed, and v is 4e to the power of x. Differentiate u, 6x squared, differentiate v, which is itself. We've seen this in the product rule. Here's the quotient rule, and we just slot the 4 bits in as before. So it's v by du dx minus u by dv dx, and all divided then by v squared. Numbers do what numbers do, powers do what powers do. Remember to line up your answer in terms of number, highest power on x, and then e to the power of x. That's always the order. So numbers do what this will be 24x squared e to the power of x. 4 by 2 is 8, x cubed e to the power of x. 4 squared is 16, and e to the power of x squared, remember, e to the power of x raised to the power of 2 is e to the power of 2x. And finally we look for, so this is the correct answer. It is neat, just could be a little bit neater. We look for something that's common to all three terms. And we can see that 8 e to the power of x is common to each term. And when we divide each term by this, remember each term, there's 3 terms, 1, 2, 3. Each one must be divisible by whatever we're cancelling. We end up with this, which looks a lot neater, I think you'll agree. And now we'll take a look at the chain rule. So if an expression to be differentiated consists of a composite function, composite function written in maths looks like this. It's essentially a function acting on another function. So here we have a function in x, and it's been acted on by another function. Then we use the chain rule. So a composite function is a function in x. Now I've written the function in x in blue throughout to try and help you kind of identify it immediately. And the function in x is the bit with x in it. So once you see a few examples, I hope the process will be fairly straightforward. So here we have a function in x. And now that function in x has been subjected to another function which is cubed. So this is the fx, and then g bit is the cube. That's g of fx there, the cubed bit. When you write it out mathematically, it tends to look a bit confusing, but once you get used to it, that function notation is quite useful. Here's another one. So here's the function in x, sine 4x is the function in x, and it's been acted on then by the function sine. Minus 2 natural log of 1.6x cubed, there's the function in x, and it's been acted on by g, which in this case is the natural log. Here we have two composite functions. There's our function in x, there's the g bit, there's our function in x, and there's what's acting on it. So the function in x is easy to spot. It's the bit with x in it. Here's another one. 5x is the function in x, and the kind of other function that's acting on it is e. So in each of these examples, the function in x, fx, is blue. And fx is the bit with x in it, just to kind of, I know I'm not stating the obvious, but just the x bit is the function in x, and then whatever's acting on it is g of x, as they'd say, g of fx. There's g of fx there, that's how you'd say it. So once we've identified that the function is composite, there's 2 steps to using the chain rule. The first step is differentiate this bit, the outer function, g, but leave fx untouched. That's your first step. So we differentiate g, but fx stays exactly as it's written in the problem. Then the second step is to differentiate fx and multiply it by our answer from step 1. So there's f of x, f dash x, that's the derivative of the blue bit, and it's been multiplied by step 1. So I know, guys, it's beginning to look a little bit complex now. Unfortunately, maths can kind of head down these kind of pathways very quickly. But I hope once you see a few examples, it'll make a little bit of sense, and you'll be able to kind of use the chain rule quite adaptively. It's quite easy. Once you know what you're doing and the steps to take, it's quite a straightforward process. It's definitely, I would argue, much easier than the product rule or the quotient rule we saw earlier. So best explained by example, as always. So here we have a function. Now I hope you'll see there's an x bit. That's our f of x. I should write this in blue. There's f of x, and then the g bit is the cubed. That's g there, and there's f of x. So first step, identify the function in x. Well, that's this bit here, so in the next line it's colored in blue. So that's your first step. Now we've identified it as a composite function. So now step 1 is to differentiate the cubed, and remember, anytime we have a power, we bring down the power and we reduce the whole power by 1. So that's step 1 done. But the key then is to leave fx alone. So differentiate the outer function, like I said, the power. So the power comes down and we add -1 to the whole power. But notice how fx is still untouched. Now the next step is to differentiate this blue bit, just using the normal rules, and multiply it by step 1. So when we differentiate this bit, this comes to 6x minus 4. So here's step 1, and there's step 2. And finally now there can be a little bit of tidying up. This bracket here moves to the front, where each bit is multiplied by 3. So the 3 multiplies by this bracket, but the bracket has moved to the front. Tidy up the function where possible. So the 3, so it's 6x by 3, that gives me 18x, minus 4 by 3 gives me the minus 12. And fx, generally you don't try and square this out or anything, or expand it, as they'd say, just leave it. This is probably the neatest way of writing this function. Here's another example. Find the derivative of this function. Well, I hope you can see there's the function in x, and then here's the outer function. So step 1, identify the function in x. We write it in blue. There it is. Step 1, differentiate the outer function. So we're going to differentiate the 2 sign bit. When we differentiate the 2, that stays where it is. I'll just try and change the colors a bit more. When we differentiate sign, we get cos. Now we leave fx alone. So that's step 1. Now step 2 is to differentiate 4x, which is 4, and we multiply it then by step 1. Differentiate fx, multiply by step 1. So the derivative of 4x is 4. And finally now, tidy up the function. That 4 comes, remember, numbers always float to the front. This 4 here, guys, is sealed in by the cos. So you cannot mess around inside that cos bit. That's kind of sacrosanct. The only way you can start to play with that 4x in blue you have to get rid of the cos first, and it's a whole different process than what we're looking at the moment. So the 4 at the end just moves to the front, and we get 8 cos 4x. And remember, this is the slope function. This will give us the slope at any value of x of this function here. So it's very powerful. Calculus is a very powerful tool, and it allows whole new layers of information to be determined about a function that wouldn't be available from this function here. This one looks a little bit more complicated, but don't let the decimals put you off. The process is the exact same. Numbers do what numbers do, functions do what functions do, powers do what powers do. First step, identify the function in x. That's the bit with x in it. Next step, differentiate the outer function. So we're differentiating natural log, remember, and it's on the first page. If y is equal to ln x, its derivative, dy dx, is 1 over x. So we've identified the function in x, and now we're going to differentiate this bit. The constant still stays, so the minus 0.2 is going to be in our answer, but it's going to be minus 0.2. That stays. The natural log, when we differentiate natural log, anything that comes after it drops below the line. So if we were to differentiate the natural log of 4, dy dx is simply going to be 1 over 4. Differentiate the outer function, leave fx untouched. So like I said, the constant stays, f of x stays, but then this under the line bit, that's the derivative of natural log occurring. Hope that makes sense. Now our next step is differentiate this bit. The 3 will come down, multiply by the 1.6, that'll give us 4.8. And then we add minus 1 to the old power. So here, this is the derivative of this bit here. And finally then, tidy up as much as you can. Remember, this can be written as a fraction, top by top, bottom by bottom. So 0.2 by 4.8 gives us 0.96 x squared with the minus. And finally then, numbers do what numbers do. Cancel as much as you can. It still must be minus, guys. It's a negative fraction. It's a minus divided by a plus. So regardless, your answer is going to be negative. Numbers do what numbers do. And powers do what powers do. So you can see the derivative ends up looking actually quite neat compared to this answer here. But it's important to realize they're both the same. It's the same, they're equivalent functions. So don't let it put you off, guys. It is kind of quite complex, the chain rule, but once you understand the process, it's fairly straightforward. Don't always expect nice, neat answers like this. Very often your answer won't simplify from this bit here, and you just leave it as it is. If you're ever unsure, just leave this function and don't cancel too much. There's nothing worse than cancelling too much and bringing errors into your work. So now we're just going to take a look at differentiating exponential functions, because these are the ones scientists deal with the most. And if you remember from the previous lecture, with an exponential function, at any point x on the curve, the y value equals the slope at that point. So that's what it means when we say if our function y is equal to e to the power of x, the derivative is itself. So this is the slope and this is the output. So this tells us what the output is for any value of x, and this tells us what the slope is for any value of x. So if the output is 1, then the slope is 1. When y is 1, the slope is 1. When the output is 5, the slope is 5. When the slope is 10, when the output is 10, the slope at that point, if we were to draw a tangent and get the slope at that point would be 10. And like I keep saying, guys, the exponential function, especially this e to the power of x, this is a function that occurs very, very regularly in science, because in science we're often looking at how something grows naturally or reduces or decays naturally. So here's our exponential growth function. We'd use the chain rule, so just in general, this is the mathematical version of that function above. Both of these are the same, just with different letters. I know they look completely different, but they're actually pretty much the same. This is kind of the science version, and this is the mathematician's version. Now, if we were to differentiate this one, there's our function in x. So dy dx, first of all, the constant will stay. When we differentiate e, it'll stay, and our function in x stays. So it looks the exact same. That's step 1. It's kind of the same as our original. Next step, though, is to differentiate the function in x, which will be bx to be differentiated, just gives us b. Finally, then, we end up with b by a, bring the numbers together, b by a, and e to the power of bx. So now we'll take a look at a few examples of differentiating exponential functions. We're hitting the end of the lecture now, guys. You'll be glad to know. It is tricky, guys. I'm sure you're kind of holding your heads at this stage and crying, but you are in college, you are studying science, and this is maths. So it's not a good combination. So now we'll just take a look at a few examples of the chain rule being used to differentiate exponential functions. Find the slope of 4 by e to the power of 5x at the point x is equal to 0.3. So first of all, identify fx. There's the x bit. Step 1 from the chain rule is differentiate the outer bit, differentiate 4e to the power of. Differentiating the outer function, that's just what I'm showing there. And it actually stays the same, because that is the principal property of the e function. Its derivative is itself. Now step 2 of the chain rule is to differentiate fx. So when we differentiate 5x, we get 5, and multiply it by this step that's on the screen. So we simply multiply here by 5. And finally then, tidy things up, the 5 moves to the front, and we end up dy dx is 20 e to the power of 5x. So very often with these, you can just simply differentiate that bit there and multiply it by the start, and that'll get you there very quickly. So now we're going to feed in. We're interested in, this is the slope function, remember? So we just feed in now, at x is equal to 0.3 into this. And then just get your calculator, and we can then work out the slope at that particular point. And if we wanted, guys, we could go to 10 decimal places here. It's no problem. Just feed it in and you will get your answer bang accurate to 10 decimal places. Far more effective than drawing tangents, drawing graphs, anything like that. This one looks a little bit more complicated, guys, but the exact same process. We want to find the derivative of this function. What's the slope of this function? The rate of change, I'm calling it this time. Same thing. Rate of change, slope, same. They mean the same thing. And we're interested in what the slope is at this point here. So first of all, identify our function in x. I think it should be fairly straightforward. It's the bit with x. Now we want to differentiate this bit, which is itself. We leave fx alone. That's what this is saying. So we're getting the derivative of the outer bit, the 1.6 e to the power of, which is itself. The derivative of that is itself. Leave fx alone. Don't kind of immediately. Sometimes people dive in and differentiate this as well in the same step. That's incorrect. Fx must stay untouched in the first step. In the second step, we now differentiate this. I hope you'll agree. It's 8x plus 3. And that'll then be multiplied by step 1. And there it is. Finally then, this bracket moves to the front and we multiply everything in the bracket by 1.6 and we get this. So 1.6 by 8 is 12.8, 1.6 by 3 is 4.8. That's all that's going on there. On the next slide now, we'll kind of take a look at that, take a look at the slope at this point. So there's our derivative from the previous slide. At x is equal to 0.2. Feed these values in. Obviously dive for your calculator straight away. Just be careful entering all the values, guys, but modern calculators kind of try to make it at least as error-free as possible. And we end up with the slope of the function. So this is quite a complex function. But without even drawing a graph, we can now tell what the exact slope is at any point we're interested at all. So that finishes us up for this lecture. I realize it is a bit long, but I hope it makes sense. It's just one of the essential parts of teaching calculus. You always have to teach the product, quotient, and chain rules. I don't particularly enjoy them myself, but they're just one of the necessary evils of learning maths, and particular learning calculus. So thanks again for bearing with me, guys. Stay safe and we shall chat to you soon.